Hi everyone, welcome to the sixth lesson for topic 3.3 Graphs and Networks. So this is also the last lesson for this topic. So just a very quick recap on all the 5 lessons that we have learned previously. So in the first lesson, we covered the part where we discussed about the different elements in a graph. So which you are introduced about the different terminology like edges, vertices, loops, multiple edges, faces, and so on. Then after that, we also talk about the different types of graph. So all this terminology prepare you to learn all the further content, right? So you learn about what is that meant by a complete graph, a connected graph, then what is that a bridge, then after that what is a bipartite graph, then what is a weighted graph, and so on. Okay, then after that when we move on in the second lesson, we talk about planar graph. So I hope that you still remember. So it's a graph that you can be drawn on a plane without any edges intersecting each other. So in planar graph, then we use Euler's rule to help you to check your answer to see whether the graph is already been drawn into a plane or not. Okay, then after that in the third lesson, we talk about different type of walk. Alright, so you learn what is that meant by a walk, what is a trail, what is a path, what is a cycle, and so on. Then after that, after walk, then we learn about different type of connected special walk that you have in a connected graph. Then we learn about what is that meant by Eulerian, semi-Eulerian, Hamiltonian, and so on. Okay, then for the fifth lesson, which is the one that we end before the semester, then which is the shortest path. Okay, sorry, I do not have any place to write, so I'll write here. So shortest path. So how can you find out a road in a path in your graph so that it will give you the minimum distance, the minimum time, or the minimum cost that you require, depends on the situation that you have. So these are all the things that we have learned so far. And in the last lesson, we are going to talk about adjacency matrix. Okay, so that's the keywords for today's lesson. So I just want you to remember that you will need to know how to construct an adjacency table, no matter it's from a normal graph, it's like a non-directed graph, or from a digraph, which is a directed graph. Then you will need to use the matrix to help you to solve some problems. Okay, so that's basically what we'll cover in today's lesson. All right, so let's start with the content. All right, first of all, what is that meant by a adjacency matrix? So graphs can be represented by using an adjacency matrix. So you can think of it in this simple way is that adjacency matrix is basically the other type of representation of graph. So which means that instead of using a graph to represent the information that I have, I use adjacency matrix. So which means that it's supposed to be two-way process. So which means that you are able to construct a adjacency matrix from the graph, then you should be able to construct a graph from an adjacency matrix as well. So because they are both a representation. Okay, so an adjacency matrix is a matrix with rows and columns containing numbers which represent the number of edges connecting the vertices. Alright, so it seems a very long thing, but later when we try to construct the adjacency matrix, you'll understand it better. Okay, so something that's important is I want you to remember that all the metrics that we are dealing with for this chapter will be all square metrics. So the idea is that a graph containing n vertices is represented by using an n times n matrix. In an easier way, if let's say you have a graph with 3 vertices, then which means that you are using a 3 times 3 matrix to help you to solve it. Okay, so basically, yeah, you can see that no matter how many vertices that you'll be having, then you should be having like the same number multiply the same number matrix. So if you're, you will be using like 3 times 3, 4 times 4, 5 times 5, it all will be square matrix only. Okay, so some important notes before we move on to the construction is that even though a loop is counted as 2 when you are calculating the degree of vertex, so remember that for adjacency matrix, loop is only counted as 1 edge. Okay, so you can remember the idea is that when we talk about adjacency matrix, right, later we'll try to connect it to length of walk. So no matter you are walking from D to D, or you go to this way or you go from the other way, is all from D to D meant for adjacency matrix. So that's why remember that loop only count as one edge in adjacency matrix. But when you are calculating the degree of vertex, is calculating at two, like one in, one out. Yeah, the thing that I explained before. Okay, so remember, loop only counted as one edge for this lesson for adjacency matrix. Alright, so now let's move on for the part where we are going to construct our adjacency matrix, and we'll be looking at two types of graph. The first one is non-directed and the second one is directed. Alright, type 1. So as you can see that there's no arc, so meaning that there's like no arrow in the graph above. So which means that this is a non-directed graph. Why didn't I use the word simple graph? Because you can see that there's multiple edges and loop. So it's basically a graph without any direction. So that's why in this case, the type 1 that we'll be looking at is the normal one, which is like the one that without any direction, so which is known as non-directed graph. Okay, so now let's try to construct our adjacency matrix. Okay, it's not going to be very hard, but just make sure that you're following, then you should be able to do that. Alright, so we'll try to use M to represent all the matrix here. So it doesn't need to be M. We can use any alphabet. It's just like unknown. It's just like a variable that you want to use. So if you want to use A, B, C, D, also can. But A, B, C, D now representing the vertex, right? So it'll be good that you use other. So in this case, we are trying to use M stand for matrix. Okay, so you remember now the first thing that you need to check is how many vertices that you are having. So in this case, A, B, C, D. So you have 4. So which means that you are going to create a 4 times 4 matrix. Alright, a 4 times 4 matrix. So in this case, we will have 4 row and 4 column. So how can you start with that? Then we write down all the vertices that we have. So for example, we have A, B, C, and D. Alright, then we do the same thing for the column. So A, B, C, and also D. So now you can put in the bracket. So make sure that it should be a straight one. Alright, okay, so after you have prepared this template, so now you remember that when you start from a row, it tells you that what is the direction from. So this is for your own explanation. After you understand it, then you doesn't really need to write. So this is the way from. Okay, so this is the way to. So for this part, is not so important yet because when we are talking about a non-directed graph, you know that it should be a two-way graph, right? So you can travel from A to C, you can also travel from C to A. But this from and to is very important when we move on to type 2 later. Okay, so now by writing down this guideline for you, then now we can proceed to fill in the blanks here. Okay, so how can we do that? So all the numbers that you are putting in the cell here, representing the number of vertices connecting the vertices in your row and column. Okay, so in an easier word, when we try to put at this, so you can see that at this place is the intersection of row A and column A. So now by looking at the graph, is there any edge connecting A to A? So you can see there's no loop, am I right? So that's why there's no edges connecting A to A. So that's why 0. So now move on to the second one. So from A to B. So same thing, you ask yourself, so how do I know it's A from B? Because you see at this place is the intersection of row A, column B. Am I right? So that's why by looking at this, then I know that I need to find from the graph here. So is there any edges connecting A to B? Yeah, there is one, right? From A to B. So 1. Alright, move on to now. This part is the intersection of the row A and column C. So that's why A to C. So you realize that there's 1, there's 2. So that's why 2. Okay, 2 edges connecting connecting A to C. So for D now, is there any edges connecting A to D? Yeah, so you can see that's 1, so that's why 1. Alright, okay, so now let's move on. So we are at the row B. So you can think of it as if how many edges from B to A, how many edges from B to B, how many edges from B to C, how many edges from B to D. So, or you can try to look at the intersection. So this is the intersection of row B, column A. So that's why I'll be finding what are the, edges that connecting B to A. So B to A, so 1. So you'll realize that for non-directed graph, right, you should get the same answer when you are trying to check, no matter you are talking about, you see, from A to B is 1. So that's why from B to A should be 1 as well, because it's a two-way thing. A to B is 1, then B to A should be 1. So same thing when we move on. So B to B is a loop, right? So that's why, you do not have any loop at B, so that's 0. So B to C, we still didn't do anything about that yet. So you can see B and C is not adjacent to each other. So that's why it's 0. So you can see that why is this called as an adjacency matrix? Because it tells you that what are the edges that is adjacent between the vertex. All right. So now D, so from B to D, yeah, that's one edge. So that's why 1. Okay, so I hope that by now you can see some pattern here. If let's say I'm trying to look at this row first, this column first, then what do I realize is that when I try to see from C to A, it should give me the same answer where C to A and A to C. So it's supposed to be 2 as well. When I try to look at this part from D to A, supposed to give me the same answer when I try to look at A to D, which is from this part A to D or D to A. So it's supposed to be 1. Okay, so later we are going to talk about this mirror image kind of thing. You can see 1, 1, 2, 2, 1, 1. Okay, now let's try to fill in the blanks for the other one first. So A, C to B. So C and B is not adjacent to each other, so that's why 0. So C to C, there's no loop at C, so that's why 0. So C to D, so they are not adjacent as well, so that's why 0. After you write down, then you can always check. For example, the total for C is only for this part. Yeah, that's correct. Because for B and D, they are both not adjacent to C, only A. So that's why you have only like one cell that's filled for this row. Okay, then for D, so D to B, that's 1. D to C, that's not adjacent, right? So 0. D to D, you can see that's one loop, so that's why that's 1. So something that you can realize here is that you can imagine if let's say there's no loop here, right? Then you will realize that for this line, you should be having all 0 because these are all the part where the same edges go, the edges go back to itself. So from A to A, 0 because no loop. B to B, 0 because no loop. C to C, 0, no loop. So D to D, why there's 1? Because there's one loop that allows D to go back to itself. So that's why this line, there's a special name for it, which is known as the leading diagonal. Okay, so what is it so special that we will need to know this term? That's because of, you can try to write it here, leading diagonal. Okay, so what is that so special is that just now we're talking about the mirror image that you can see, right? Okay, along this leading diagonal, you will realize that the matrix give you a symmetrical image. You can see 1, 1, 2, 2, 1, 1, 0, 0, 1, 1, 0, 0. Why is that so? Because it's a thing that I explained just now. B to A is supposed to be the same with A to B. C to A is supposed to be the same with A to C. D to A is supposed to be the same with A to D. So that's why it will give you something like a mirror image when you try to refer to like this is like a triangle, this is like a triangle. So this triangle is like the image to each other. You get what I mean, right? So that's why you will realize that for non-directed graph, the matrix, the element in a matrix, so what is that meant by IJ is that, for example, if let's say in this case, yeah, let's use the example of 2 because that's the special one, right? Okay, so 2 is at the place of AC, so which means that row A, column C. Are you okay? So row A, column C, so that's why it's called as MAC. It's like the element at the row A, column C. So that gives you 2. Then after that, the same thing when I try to check here. So at the row C, column A, it will give you 2 as well. So you can see that MAC will be the same with MCA. So this is what is that meant by IJJI here. So when I try to compare to this, then you realize that BC is the same with CB. Okay, so because of these properties, so that's why for all non-directed graph, you will realize that the adjacency that you produce here, right, will give you a matrix that is symmetrical about the leading diagonal. Okay, so remember that please do not only write, if the question asks you something that you need to explain something like this, then which means that make sure that when you are writing down your answer, right, make sure that you are writing down the full thing. So it's symmetrical about the leading diagonal. Because when we talk about symmetrical, even you can cut in half, then you can, you are able to fold it into half, then you say that these matrices are symmetrical, right? But if I cut it into half, it isn't symmetrical, like this is 1, this is 2, then 0 and 1. They didn't give you any mirror image. But then the only symmetrical is actually happen about the leading diagonal only. So make sure that when you are giving the explanation or you are giving the answer, so make sure that you are writing it in full. So it's symmetrical about the leading diagonal only. All right. So I hope that you have an idea how is that, how is this whole thing works. Okay, so now let's look at type 2. All right, so we are going to do the same thing, which is construct the matrix, but now for type 2, which is a directed graph. Okay, because you can see that there's arrow, like the edges here are all arcs. I hope that you still remember the edges with the arrow is called as an arc. Okay, so it's a directed graph which called as digraph. All right, so same thing. I think we can go slightly faster because you already know how to, construct. You have a good idea on it. So same thing, we have 4 vertices here. So that's why A, B, C, D. Okay, and then for the column as well, A, B, C, D. All right, so the to and from, if you can understand, then you doesn't really need to write it anymore. Okay, so now remember, you can't do it like how we did it just now because the direction here matters. So which means that when we talk about from A to B, it's supposed to be the direction from A to B. So in this case, you can see, okay, sorry, let's do A to A first. So A to A, no loop again, so that's 0. So maybe we can try to write for the leading diagonal here. So B to B also 0, C to C also 0. From D to D, you can see that's 1. So remember, loop is counted as 1. Okay, so one direction here, so that's 1. Okay, so now let's try to fill in the others. So from A to B, remember that you must make sure that the direction is in a way where what you want. So this is from A to B. So that's why, do you see any arc? Yes, so from A to B in the direction that you want. So that's why it's 1. Okay, from A to C. So how many you can see? Yeah, that's only 1. So this one is not calculated. This one is not included. Why is that so? Because these edges allows you to travel from C to A, not A to C. So that's why in this case, AC only 1. So you see there's a difference or when you have a direction or not having a direction. So the last one from A to D. So is there any edges? No, because these edges allows you to travel from D to A, not A to D. So that's why that's 0. So B to A, so same thing. This from here to here, there's no arc, so that's why 0. Because this is from A to B, right? Then from B to C, they are not adjacent. So, and then from B to D, so that's nothing because this is from D to B. So that's why that's 0. So now the next one for C. So you realize that for C, that's the only arc that going out from C to A. So that's why that's 1. Then the other one, you can see that there's no connection. So that's why you can just put in 0 lah. Okay, then now for D. So D to A, that's 1. And then from D to B, can you see anything? So yeah, D to B, that's 1, right? Then from D to C, they are not adjacent, so 0. D to D, 1 for the loop. All right, so something you can always try to track for the directed graph. For the non-directed, you can always check also. Okay, let me try to do this. So for directed graph, because you know that every of these edges with the arc, right, basically just mean one. So you can try to see, you can try to, adding up all the numbers that you have. So 1, 1, 1, 2, 3, 4, 5, 6. So you should be having 1, 2, 3, 4, 5, 6. Okay. For non-directed graph, you can check as well, but it's a little bit harder because you know that it's an image. So that's why when you are calculating it, you should be calculating without any repetition. So which means it should be this part because this is a loop, right? So it's not having any mirror. So that's why we'll see 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. That's correct. Okay. So why do you have this, the other number? Because it's it's two-way. So that's why you have like double of the numbers that you have. All right, so come back to this. So you realize that something that's different is that you are still having a leading diagonal. I mean, for any square matrix, you have the leading diagonal. But when you try to look at this leading diagonal, it will not give you any mirror image anymore. For example, from C to A to C, you can still see that because that's like A to C, C to A. So easy one from A to B and then from B to A. Okay, why is that so? Because that's direction. So when you have A to B, it doesn't mean that you have B to A. So that's why this is 1 and this is 0. So in this case, you can see that for your element, right, is no longer like AC equals to CA. So that's why for the directed graph, the adjacency matrix that we created is is asymmetrical. Okay, so basically meaning that that's not symmetrical lor. Yeah. So this is something that you can try to check, especially if you need to, if you are given an adjacency matrix, then you will need to draw a graph. Then this is something that's helpful that can help you to determine beforehand whether do you need to put an arrow or not. Okay. So later in the example, we have two questions like that, then you can try to identify from that. Okay, so some extra notes before we end here. Okay, so when we try to look at the adjacency graph, so which means if let's say you are writing a 0, meaning there is no edges connecting the pair of vertices. Okay, so if you are writing 1, then which means that there's one edge connecting the vertices. So remember when we are talking about non-directed, then it can be two-way. If it's directed, then make sure that when we are saying connecting, then it's the direction that you want. Okay, so a number that greater than 1 indicates that they are multiple edges connecting the same vertices. I hope that makes sense, which means that, for example, in this case, when you are having a 2, it basically means that from C to A, there's two edges. Am I right? So that's why when you have two edges or more, it basically meaning that you have multiple edges at that place. So for directed graph, it's harder to look at this, and this is not really called as a multiple edges in a sense, because from this is just from A to C and C to A. You doesn't have like two or more edges connecting the same pair. Okay, it's different direction lah basically. Okay, so the one in the leading diagonal, so just now we said for the leading diagonal is not all intersection with the same row and same column. So A, B, C, D, D. So which means if let's say you have a 1 in the leading diagonal, meaning that there's a loop. Okay, if let's say you're having a clean leading diagonal that's 0, 0, 0, 0, meaning that in your graph itself, you shouldn't be having any loop. All right, so that's the idea. So now let's try to look at example 1 and 2, and basically we are just going to practice what we have done here to draw to create a adjacency matrix again, then use it and look at some adjacency matrix that's given, and we try to draw a graph. All right, so I hope that by now you should have at least a rough idea on how to do this, right? Okay, so if let's say you're okay with it, then you can always try yourself. Then after that, you can play with like double speed. Then after that, you try to check the answer. Okay, so yeah, same thing. So let's try to start with writing down the vertices for the row and column first. All right, so now let's check from the graph. So for A to B, A, you can see there's no loop. Yeah, basically when you see that there's no loop in the matrix, then you can write down all 0 in the leading diagonal. So I mean you have, for example, this is a 4 times 4 matrix, right? You have 16 entry. So maybe you will prefer to, write as a mirror thing, or you'll prefer to write down row in row. There's nothing right or wrong. But the idea is that just make sure that you are doing it efficiently enough, then try to make sure that you can avoid any careless mistake that will occur in the process itself. Okay, so it just depends on your own style and then your understanding about it, and you can decide how you want to go with it lah. Yeah. Okay, because if you want to do like randomly, you want to look at A, then after that do everything, then you look at B, then you do everything, then you look at C, do everything. So, or you try to look at the matrix and you want to write down in a mirror, so depends on how you want to do that. Okay, so A to B, so that's 2. A to C, that's 1. A to D, that's not adjacent to each other, so that's why that's 0. Okay, then after that for B, so B go back to A, that's 2. So B to C, not adjacent. B to D, that's 1. Okay, then after that for C to A, that's 1. C to B, not adjacent. C to D, that's 1. Then for D to A, that's 0. D to B, 1. D to C, 1. Okay, so if you are doing everything like this, then you can check it after you finish the whole thing and see that this is your leading diagonal. Are you having a matrix that is symmetrical about the leading diagonal? So if you are not having something like this, meaning that your answer, there's something wrong there. Okay, so you can see that in this question there's no loop, so that's why for your leading diagonal is all 0. All right, yeah, so that's the idea how you can do that. Okay, so now for part B. So I'll try to go a little bit faster for this one to show you an easier way to do, especially something like this, because you can see that there's a lot of part that, for this graph, right, it's a disconnected graph, which means that you can see that you have, as if you have like 1 part, 2 part, 3 part, and they are all not connected to each other. You get what I mean? So you can imagine that in the graph, something like this, right? The adjacency matrix that you are going to produce will be having a lot of 0. Because a simple example, when I try to look at A is only adjacent to E. So that's why there will be only a number 1 from A to E. Then the other will be all 0, right? So you can check for the other, it will always be the same as well. So that's why you can go a little bit faster by using a method, something like this. So A, B, C, D, E, F, G. No worries about the space, because for the last one you will only need 4. I believe that you should be able to having the sufficient space for that. E, F, G. Okay, so the efficient way to do that is that I don't recommend you to do this for all the questions, but for question like this, that you can imagine that you have a lot of 0, you can do something like this. So like what I said, you can see that only E is adjacent to A, so you can imagine that for the row of A, only E will be having 1. So you do not need to really look at 1 by 1 already, right? Then you know that all the other will give you 0. So same thing when you go to B, B is only adjacent to D. So that's why B to D, this is 1 here. Then the other one, you know that it will be all 0. Okay, sorry, make sure that I try to write a little bit better. All right, then now for C, C is only adjacent to D. So CD, so it's 1 here. Okay, so that's why 0, 0, 0, 0, 0, 0. Something that you can check is that you see there's 1, 1 for D here, then you try to check that, yeah, D is adjacent to 2, so that's why you see there's like two field cell for the column D here. Okay, so for D, yeah, you can imagine lah, it will be 2 as well, so B and C, so B and C 1, 1, all the others 0. Okay, then after that for E, then is connected to, is adjacent to A, and there's 2 edges connecting to F, right? So that's why E to F, it will give you 2. Okay, so the other all not adjacent. Then for F, So it's only going to going to E, and then there's multiple edges as well. So that's why 2. Okay, so 0, 0, 0, 0, 0, 0. So for G is an isolated vertex. So that's why in this case it's not adjacent to each other, it's not even connected to any other vertex. So that's why everything here is 0. So after you check it, then same thing, this is a non-directed graph, and it should give you a graph that's symmetrical about the leading diagonal as well. So that's why you can see 1, 1, 1, 1, 1, 1, and 2, 2, then all the other are all the same. Okay, so there's no loop as well, so that's why for a leading diagonal, it should be a clear 0. Alright, so part C. We do one more for a directed graph. So same thing, you can see it's quite complicated, but it's actually having a 4 vertices only. Alright, so remember when you are looking at directed graph, direction matters. Okay, so from A to B, there's only one, so that's why this one you can, cross it off as well. There's no loop from A to A, so A to B, that's 1. Okay, so A to C, no, A to D, no, so 0, 0. So from B to A, so B to A, that's 1, you can cross it off as well. Then from B to B, that's one loop, right? So that's why it's 1 here. Okay, B to C, is there any? Yes, so B to C, 1. B to D, no, because this is from D to B, so B to D is 0. Then after that, when you check from C, so C is adjacent to everything except 1A, so A is 0. And then from C to B, there's 1 here. From C to C, no loop, 0. From C to D, there's 1, 2. Okay, so that's why 2. After that, D to A here, there's nothing. D to B, that's 1. Okay, D to C, that's 1 also. After that, D to D, no loop, so 0. Okay, so something that you can check: 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's why 1, 2, 3, 4, 5, 6, 7, 8, 9. So which means your answer is correct. Same thing for this one, you can check, but you check, half of the leading diagonal, 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, 6. Oh, something wrong. Sorry, this is not 1, 2, 3, 4, 5. Okay, so 1, 2, leading diagonal is here. So 1, 2, 3, 4, 5, and that's correct. Okay. Alright, so that's basically the part where how you construct an adjacency matrix. So I hope that you should be able to do that now. So now let's move on to example 2. Okay, example 2, use the following adjacency matrices to draw a corresponding graph. So in this case, yeah, something that will be helpful is check whether it's symmetrical about the leading diagonal or not. Then from there, you'll be able to know whether it's a non-directed graph or a directed graph. Then it will be helpful for you when you try to draw it. Because you doesn't want to draw at the end and realize that, hey, you should put in the arrow or so on. Okay. So in this case, we have 5 vertices, so it's easy that we just start with putting in the vertices that we have. So A, B, this is not the only answer. You can, do anything as you like, as long as the thing that you are connecting later are all correct. Okay, so A, B, C, D, E. So now let's start from, let's check the graph first. So you can see that definitely you see there's only 1, 2, and this is 0, then you know that this is not symmetrical. So which means it should be a directed graph. Okay, so and you can see here 1 and there's no 1 here. So that's why it's definitely a directed graph lah. So let's start from A. So from A to B, that's 2. So we can try to draw from A to B. So remember your arrow. Then after that, B, A to B, another 1. Okay, so that's 2. All right, then after that, from A to D, that's 1. So A to D, that's 1. All right, I hope that you're following. Okay, then you settle the row A already. So now for B. So B is not adjacent to the other except for E. So B to E, that's 1. So B to E, that's 1. Okay, then after that, move on to the row C. So C is only adjacent to D, then it's C to D. So C to D, that's 1. Okay, move on. D to C, that's 1. D to C, then you need to go back. Okay, then after that, D to E, that's 1. So D to E, that's 1. All right, then after that, next one, E only adjacent to B. So E, go back to B. So this is supposed to be your graph. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 8. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, sorry. Okay, so that's why the answer is correct. So make sure that you are having all your vertices in a clear dot. Okay, so that's basically the thing that we'll obtain. So make sure that you are, putting in all the directions. So make sure everything is correct. Okay, so part B. So now when we try to look at this same thing, you have 4 vertices. So let's identify whether it is a directed graph or non-directed graph. So in this case, link diagonal all clear, so which means no loop. Then after that, you can check, yeah, it's a mirror image, right? You can see it's symmetrical. 1, 1, 1, 1, 1, 1, 0, 0, 0, 0, 0. Okay, so that's why in this case, it should be a simple graph. So, it's okay. You can always try out, then you realize that it's not a simple graph, then you erase that, you do it again. Yeah, basically that's the idea. Okay, so A to A, no. A to B, 1. A to D, that's 1. Then when you go to B, B to A, that's 1. Okay, B to A, that's 1. So remember, you don't draw the other edge because that's basically A to B, B to A. So that's why mirror. So B to C, you have 1. So B to C, 1. Okay, then for this part, then this should be a mirror lah. Then you should not be drawing any extra edges anymore. So C to B, so that's why C to B. B to C, C to B, so mirror B C C B. Okay, then the last one here should be the same. So A to D is the same with D to A. So that's why 1 1. So D A A D. So this is basically the graph that we are having. So when you are calculating it, then basically leading diagonal, right? So there's nothing to add. So 1, 2, 3. So that's why 1, 2, 3. So that's why that's correct. All right. So remember that there's no, it's not one answer only. If you are doing something like, A, B here, and then C, D here, you get what I mean? Then you will have A, B connecting each other, then A to D, and then B to C. It's actually the same thing as well. It doesn't matter that whether you are following my shape or not. So what is important is you're having the correct vertices and correct edges that connecting the vertex to the right connecting the edges to the right vertex. Okay, so that's basically the part. So now we are moving to the next part of the notes, which is also the last part of the notes, which we talk about reachability. So let's move on. Alright, so reachability is the ability to get from one vertex to another vertex in a graph. So, you doesn't need to memorize this form. It's just basically the title. You doesn't really need to know this in the syllabus as well. What is important is the content after this. Okay, so what is that meant by the matrix? So later we are going to look at your original matrix, and what happened after we square the matrix, what happened after we cube the matrix, we put in different power, then what is that meant? Okay, so in this case, what is the mn mean? So the matrix to the power of n show you the number of what of length n. Okay, between any pair of the vertices. Okay, it seems very vague now. Okay, basically in an easier word, you can try to look at the part of the notes. So when we try to do M1, so basically it's the normal graph that we are drawing, the normal matrix that we are doing just now. Okay, let's try to write down the answer. This one is the same with the graph that we have in the first page. So just try to write down our answer according to what you have in the first page there. Okay, let's write down first, then I'll try to explain from there. Alright, I hope that I do not need to, talk about the construction again. You should be able to do that. Okay, so 0, 1, 2, 1, 1, 0, 0, 1. Alright, okay. So this is the M1, meaning that it's the original graph. We didn't square, we know like X before square, then it's like X is just X1, right? So it's the same thing. So this is M, so it's M1. Okay, so matrix to the power of 1 records all the number of walks of length 1 in a network. Okay, So you see, it's something that, that's very logical. So when you write down 1, it actually means that there's one walks of length 1 from A to B. That's correct, right? That's 1. Then after that, when you write down 2, which means that there's 2 walks of length 1 from A to C. So AC and AC. So that's both of them are walks of length 1. If you forget what is the meaning of walks of length 1, please check the types of walk. Okay, basically it's just that from A to B, you only pass through one each. So this is length 1. So if we are talking about ABD, then which means AB is 1, then BD is 1. So this is length a walk of length of 2. Okay, so if we are doing about like ADBA, then which means that's 1, 2, 3 lor. So that's walks of length 3. Okay, so when we are talking about M1, which means that it will tell us how many number of walks of length 1 you will have between the pair of vertices. So from A to B, then which means that's 1. So and AB is the answer lah. So that's 2 from A to C. So AC and AC. So AD, then that's 1. Okay. So for this part, it's actually still okay because, it just makes sense in a way where you construct this by yourself. So of course, when we talk about it's adjacent to the matrix, right, it's basically all walks of length 1. Okay, so some very cool thing come here. Okay, so when we are talking about M2, which means that it will records all the number of walks of length 2 in the network. Okay, so before we talk about that, let's try to do the calculation in the calculator first. Okay, so you can try to pause the video and grab your calculator. You should be following me step by step here. Alright, so let's look at the calculator and see how can we do this calculation in your calculator. You do not need to know this in manual. Okay, let's take out your calculator. Okay, so now when you try to having this, so add calculator. Okay, sorry, my screen here is a bit small, but yeah, okay, add calculator. Alright, so after you add the calculator, there are 2 ways that you can construct your matrix. You can try to listen first maybe, then after that we do it together. So the 2 way is the first one, go to menu, and then matrix, you can see matrix 7, then create, then press matrix. Okay, if you are using number, then which means that is menu 7, 1, and then 1. Okay, then after you press it, then you'll be able to see something like this. Okay, later we come back. The other alternative that you can do it is you can see there's a symbol here. So after you press this, then you go to this cell. So this one is meant for only 2 times 2. So in this case, we are doing a 4 times 4 matrix. So that's why you should be, always use this lah. It's easier. So you just use your, go to left, right. Okay, then after that, you just press enter. Okay, so you will get the same thing like how we create it by using the menu just now. Okay, so 2 ways, depends on you which one you like it. So menu 711, or you want to do this, then you just press this symbol, then you go and choose the icon just now. Okay, then after that you put in here. So in this case, we are building a 4 times 4 matrix, so that's why 4, 4. Okay, so now press OK. So after you press OK, the calculator will show you something like this. So how are we going to do that? Then just press everything in your calculator. So just according to your answer here. So let's key that in. So 0, then you press tab. Okay, 0, tab. Then go to the next one. You have 1, then tab, then 2, then tab, then 1. Then you can go tab again. Then it will straight away go down. Okay. So yeah, you should be having your paper together with you, right? So that's why, because I can't be able to show it side by side, it's a little bit too small. Okay, so we have 1, 0, 0, 1. So 1, 0, 0, 1. Okay, then the next row, 2, 0, 0, 0. So 2, tab, 0, tab, 0, tab, 0. Tab, go to the next one. So we have 1, 1, 0, 1. So 1, tab, 0, 1. Okay, don't press enter. Okay. So now something that's helpful that how are we going to do that is to assign the matrix. So how can we do that? So you can, just press going to the left and go back to your matrix. Okay. So your, what is that called? Your sign now should be before. Okay, this thing should be before your matrix now, or you can press this before you press the matrices also can. Depends on how you want to do that lah. Okay, so we need to assign a variable of it. So how we can do that? You can just press anything that you like. So for example, if let's say I want to do G, then I just put G. If you want to put A, then just put A. Okay, then how are we going to assign? Then you can see there's a thing like what is this thing called? It's okay lah. Then dot dot then equal to. Okay, so you just press Control, then you press here, then you will get the symbol. Is that okay? Again, let me try to backspace it. Okay, so you can press anything that you like. If you want to use K also can. Then Control, press on this, then you should be able, yeah. When you press Control, basically you are getting the one in the blue color, which is on top of each of your button, right? So Control and press this, then you'll be able to get this. So make sure that your variable here should be in italic. So if you're in bold, then which means that you might need to change another one because you have assigned that before. Okay, so yeah, make sure it's normally when you try to first use it, it should be in italic lah. If later, we are going to do different question, then in that part, you make sure that you don't repeat the variable that you will be using, because as long as you assign K for this one, then K should be this one. Okay, or else then you can open another new page. Okay, so after you do this, then only you press enter. So when you press enter, then you'll get back the exactly same thing here, then it will bring you to another row. Okay, so how are you going to do that? We are doing square, right? So that's why you just press K and then square. So in this case, either you want to use this, or if you don't want, then you can try to use E, then K, then press this, then it will give you something like this as well. Then after that, you press 2. It's the same thing, but square, you can do it in a faster way lah. Later when we go to cube, then you need to press that. Okay, I repeat again. So K and power, and then you just press 2. Then now straight away enter. So why is assigning this important? Because later you will need K cube. So if let's say in the question itself, you need to use the matrix repetitively, right? Then you doesn't really want to keep on inserting this thing. So that's why it's easier for us to assign that. Everything that we want to do is just keep on using the variable. Okay, so you just press enter. All right, enter, then you'll be able to get this. Okay, now let's copy down the matrix to the handout first. Okay, later I'll explain what is these numbers mean. All right, so let's try to write down our answer. Okay, so M2, same thing. All right, so we can write down the answer just now: 610212220242, and then 2224. Okay, so here come the thing, the so-called the cool thing. Okay, so how is this, what is this indicate in this question? Okay, so you see, when we write M squared, it records all the number of walks of length 2 in the network. So what does that mean? For example, let's start from AA. So you can see, there's a number 6 here. So it actually means that there will be 6 walks of 2 that allows you to travel from A to A. So how do you know that is correct or not? Then let's check. So when I try to do this, so this is from A to A. So meaning that I should be able to get 6 different walks of length 2 by using this network. So let's check how can we do that. So A, B, A, am I right? A, go to B, then go back to A. So it's a walk of length 2. So ABA is 1. So now we move on. So how about AD, then go back again. Am I right? So that's why ADA. Okay, so I think there's nothing else here. So that's why let's check for C. You see A, C, then go back to A. Am I right? So that's why we have ACA. Okay, Please follow one by one because I'm going to use different color here to indicate different thing. Then the other one, A, C, then go back A. I'm using different route, right? Am I right? So that's why it's still a walk of length 2. So ACA. Another color again. So if I were to using here, then you can see A, C, then go back to A. Am I right? This is a different road, so ACA. Okay, and according to this, I have 6, so which means that's one more. So I hope that you already know what's the last one, which basically go from the other way. So A, C, then go back to A. So that's why ACA. So this is how it gives you 6 walks of length too. Okay, same thing. Let's check for the other. Okay, if now I try to do it for B, A to B. So A to B is show that only one. Is it only one? Then you can check. So if you want to go from A to B, then you realize if you go from A, B, then only length 1, right? Then which means this is not what we want. Okay, then how can you reach B by a walk of length 2? So you see A, D, oops, sorry. Let me erase that. Okay, A, D, B. Is this the only one? Yes, because you realize that no matter how you walk, you actually can't. So if you want to go A, C, then you can't go to B, right? Then after that, if you are going like A, B, D, then that's the only way. If you want to go A, B, then definitely you cannot go back to B by using one more route. If you want to go from this side also, you also cannot get to. So that's why this is the only one that we can get you from A to B by using a walk of length 2. Okay, then you see A to C, that's nothing. Is it really nothing? You see, if you want a length 2, then you can't actually reach C by using a walk of length 2 because AC is only length 1. AC length 1. No matter how you walk, it actually doesn't give you anything of length 2. Okay, so now let's check for the other one. So A to C, no, none. Okay, then after that, let's check the other one. Then we have A to D. So from the matrix, we know that there are 2. Okay, so how do we know that there's 2? Then let's check. So A to D, A, D, there's only length 1, so cannot. So A, B, D, oh yeah, that's 1. Can you try to see whether you can see one more? Yeah, so it's actually from the edge. 1, and then another one. So length 1, length 2. So that's why A, D, D. Alright, so definitely from C you can't reach D with a length 2 lah. So that's basically it. So you can try to check for the others number as well. So I hope that you find it, something interesting for you. Okay, so for example, the 4 here, you realize C to C is 4. So you can check how is that happen. Yeah, that's right? CAC is the first one, CAC second one, CAC third one, CAC fourth one. So that's why 4. Okay, then after that, B to A, that's only 1, which is here. Then you realize that for a graph like this, right? This is what is that? Non-directed graph. So for non-directed graph, after you square it, you should be able to get a symmetrical graph as well. So you can see that although there's something changed in the leading diagonal, but then when you try to compare it as a mirror, right? So this triangle and this triangle will still give you the mirror image if you can realize that. So yeah, you see here and then here. Okay, you still can see like the mirror thing, 2, 2, 2, 2. Okay, because the idea is obviously if there are 2 routes that allows you to travel from A to E, that should be 2 routes that allows you to travel from D to A as well. So which means in an easier word, if I'm looking at D to A, I should be able to get DBA and then DDA. Basically, that's the idea. Okay. Alright, so I hope you'll find something interesting here. So now let's try to do for M3. You'll realize the number sometimes will get bigger. Okay, so same thing, go back to our calculator. So let's check. Okay, so when you try to do M3, now you do not need to, repeat the process of keying in all the values here already. So basically what you need to do is just K and then to the power of 3. Okay, then enter. So if you are using A, then you are using A lah. If you are using B, then you are using B. So enter, then you should be able to get the other one. Okay, so this is the one that is going to tell us this is M3. So M3 records all the number of walks of length tree in the network. Okay, so now we go to walks of length tree. Okay, so same thing, let's copy your answer from the calculator first. Oops, sorry. Yeah. It's a bit ugly. It's okay. Okay, 3, 8, 12, 9, 8, 3, 5, 2, 5, 12, 2, 0, 4, 9, 5, 4, 7. Okay, so now same thing. Maybe we can try to change the other row. Maybe let's try to look at the row C. That's 12, that's a lot. Let's only check for B, C, D lah. I don't think you have enough space, but if you're interested, then you can feel free to find out the 12 routes that you can have. Okay, so yeah, maybe from C to B. All right, so same thing, let's try to check. From C to B, that should be 2 routes. So C to B, length 3. So C to B, length 3. So 1, 2, 3. So that's why C, A, D, B. Then the other one is quite obvious lah. Basically, the other way, C, A, B, D, B also. Okay, then yeah, there's nothing else. So, okay, I just went through with you a very quickly one for the 12, then you can check out the other one. So that's the 12 one is C to A. C to A length 3. So you can see 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. Sorry. C to A, right? You see, C to A, 1, 2, 3. That's the first one. 1, 2, 3, second one, and then 1, 2, 3, third one. 1, 2, 3, fourth one, and then 1, 2, go back to A. Fifth one, 1, 2, go back to A, 6, and then the other one you can try out the loop here. 1, 2, 3, then it will be 4 already. So where's the 11? 1, 2, oh yeah, 1, 2, 3. Okay, that's 7. 1, 2, 3, that's 8. Okay, then the other 4 more, you can try it out, then find out for yourself as well. Okay, I think that's something that's pretty cool lah. Okay, so you try out for your 12. Okay, then after that, let's move on. There will be a lot to write here. Okay, then you realize that C to C is 0. Then you can try to check is that solar for 3. Then 1, 2, 3, you cannot go back to C. 1, 2, 3, you cannot go back to C. 1, 2, 3, you cannot go back to C. Even you go around 1, 2, 3, you also cannot go back to C. So that's why C to C, a walk of length 3 is no. So which means that you are not possible to travel from C to C by using a walks of length 3. Okay, so that's why C to C is none. Okay, then after that, we move on to the next one. Let's see whether we can find the C to D. We have 4. Okay, so C to D here. So 1, 2, and then 3, 4. Okay, so C, A, D, C, A, D, B, D. C, A, D, B, D. That's line 4. Sorry, my fault. Oh, just a loop. Yeah. Okay, just a loop here. C, A, D, D. So this is just now is a line 4 already. Okay, C, A, D, D. Okay, what else you can do? The other way lah. C, A, D, D. Okay, so C, A, D, D. The same thing. Okay, let's erase that. Okay, so we have 2 more. So C, A, oh yeah, C, A, B, D. Okay, 1, 2, 3. So that's 1. Then now you should be able to identify the other one already. It should be CABD as well, but from the other way. So here, CABD. Okay. I hope that's something that you can get it by now. All right, then same thing. You can try to check it out for all the others number, try to find out the roots, then yeah, have fun with it. Okay, so now then the last one here. So same thing, this is the one that in total, so you don't need to calculate it manually. So everything just do it in your calculator. So same thing, go back to our calculator. So you can just put in K. So power 1 depends on whether you want to put it up. That's okay. Plus K square, okay, plus K cube. Okay, then just press enter. So you should be able to get all these numbers. So this number is like all. So which means that it tells you everything that you are able to walk from length 1, length 2, or length 3. So let's try to write down. Okay, so something interesting about this is, sorry, this is, yeah. Can I try to change yourself there? My mistake. So this is M1 plus M2 plus M3. Okay, so after you are able to get this, then you can always check it. Then you will realize that from A to A, yeah, maybe let's play with only one. Okay, for example, the BD. Okay, so B to D. So you should be able to get 8 roads, 8 walks from B to A using one length, two length, or using the length of 1, 2, or 3. Okay, so let's try to check it out for BD. Okay, so this is BD. So definitely for the first one, only one walk, which is BD, right? Okay, then you realize for length 1, do you able to get other? I don't think so. I think that's the only one. Okay, now go to length 2. So how many we can find? Yeah, B, D, D. Am I right? So that's 1. Then after that, let's check. So do you have other? B, A, D. Am I right? So that's why that's 2. Then do you have other? No more. Okay. And the other tips that you can try to see here is like BD, that's 1. So for M1, so length of walk of length 1, 1. So walk of length 2, there are 2. Then the other 5 should be from M3. So let's check the M3. So length of walk of 3. So it's length of walk. Yeah, if we are talking a walk of length 3 or a walk with length of walk 3. Yeah. Okay, so in this case we have B, A, D, D. Okay, then after that, let's see, do we have other thing else? So I use different color here. 1, 2, 3. Okay, B, D, A. I hope you get what I mean again. So 1, 2, 3 from B to D, right? So that's why I get another one. Then after that, 3. So the other one, B, A. Oh yeah, okay, B, A. Then you go back to B, then go to D. All right, so that's B, A, B, D. So that's length of 3 as well. 1, 2, 3. Okay, B, A, B, D. Okay, let's check for next one. I think it's interesting. You can try to pause the video, then try to think of it. Okay, so here to here, 1, 2, 3. Okay, so it's go back to itself. So B, D, D, D. So which means that's a loop, right? So that's why you can just like B, D, then D, then D. Then you can get 1, 2, 3, then that's length 3 lah. Okay, then okay, and the last one here, B, D, A, D. Okay, 1, 2, 3. So that's the other one. So yeah, it's actually not easy. So you can try to spend some time to try for the other number then and see whether you can find it or not. B, D, A, D. Okay, but normally, I mean, they don't really test you on this I mean, you might still need to do this, but the idea is the question won't really need you to actually list down all the roads and so on. There might be a different way that you might need to explain what you have done so that you can try to apply in the situation. Okay, but I guess it's something that you can try to play with. So you can try to like take any number then and see whether you can try to identify all the routes from from the network itself or not. Okay, it's a pretty interesting thing to have fun with. All right, so now we'll be looking at two examples in a much more application wise. Then after that, I hope that you can have a better understanding of that before you move on to your exercise. Okay. All right, so let's look at example one for this part. All right, so two more example before we end the lesson. Okay, three, the bus routes before the landmarks A, B, C, D are shown in the graph. Construct an adjacency matrix for the graph. Okay, so I hope that you should be familiar with the process now, so you should be able to do this by yourself. So vertices, so let's try to assign it as M also. All right, so we have A, B, C, D, and also A, B, C, D. Okay, I'll fast forward this process. So please try it out by yourself. Then after that, check your answer. All right, so you should be able to get this adjacency matrix. Okay, part B, determine the walks of length 2 from B to D. So use your matrix to justify your answer. Okay, so in this case, then you can try to find it out from the network first. So what are the walks of length 2 from B to D? So you can find it out. Yeah, so the obvious one, it will be B, C, D. Am I right? So that's quite straightforward. So B, C, D. Then after that, the other one that you have is BAD and BAD. Okay, so that are the three that we can find. So you can check from the graph and see whether you can find something else. So I guess that's the only three that we can find. Okay, so 1, 2, 1, 2, 1, 2, and 1, 2. So that's three different roads. Okay, so now let's try to see how can we justify our answer. So which means that if you are able to prove that the element from B to D is giving you the number of three, then which means that there's only like three walks of length 2 from B to D. So what is the matrix that can give you the number of walks of length 2? So which means it's supposed to be m squared. Am I right? So that's why we need to use our calculator to find out our m squared. Okay, so I hope that you still remember how to do that. So in your calculator, you can try to assign first. So in this case, if let's say I want to use A, okay, then control, then press this, then I'll be able to get something like this, which I assign that A is equal to the matrix that I'm going to put in. Okay, then after that, I can just press this, then after that, this, then after that, row 4, column 4. Okay, then I build it. Then after that, let's try to key in all the data, all the element that I have. So 0, 1, 1, 2, 1, 0, 1, 0. Sorry, 1, 1, 0, 1, 2, 0, 1, 0. Okay. So after I get this, then after that, just enter. Okay. So the calculator already accept that this variable A is equal to this matrix, and I want to find A squared. Okay, then I can definitely get the answer out of it. So now let's try to copy down our answer. I'll try to fast forward this as well, so make sure that you are writing down. Okay, so how can you justify them? By looking at the element that you have. So this is the walks of length 2 from B to D, right? So you check out the row D and then column D. So that's why from B to D, there's 3 here. So that's why from the matrix for row B and column D, it gives me 3. So that's why I justify that that is 3 walks of length. Yeah. Okay, there are 3 walks of length 2 from B to D. Okay, so which means the one that we find out, so which means it's correct. So which is BCD, BAD, and BAD. Alright, so that's basically the part. Okay, so now let's look at part C. Okay, is it possible to travel from A to any other towns, including going back to A by using a walks less than length of 3? So justify the answer. Okay, so this question is like one of the example that I mentioned, which is more on the application wise. So in this case, you are not really need to find out the road, but you only need to justify that is that possible to travel from A to any other towns by using a walks less than length of 3. Okay, so first thing that we can try to think is a walks less than length of 3, meaning that it includes length of 1 and also length of 2. Am I right? So how can I get a matrix uh to let me to have the information where I have both, I included both walks of length 1 and also length 2, which is by using matrix M1 plus M2. Am I right? So after I can get my M1 plus M2, which means from the matrix, then I'll be able to see all the routes with the walk of length less than 3. Okay, so we can use our calculator to help us to do that. So same thing, go to your calculator and then A1 plus, plus A2. Okay, and enter, then you'll be able to get this. And you should be able to realize that when you try to plus them together, right, it's basically the sum of this matrix and this matrix. So 0 plus 6, 6, 1 plus 1, 2, 1 plus 3, 4, 2 plus 1, 3. So when you plus them together, then basically this is like the total walks of length that you have, which consisted of either length 1 or length 2. Okay, so that's the idea. Okay, so now let's try to copy down. So when you have A, B, C, D, A, B, C, D. All right, so let's write down the answer just now. So we have 6, 2, 4, 3. Okay, and then 2, 2, 2, 3. For C, we have 4, 2, 3, 3. And D, we have 3, 3, 3, 5. All right, so this should be the answer that you will be getting. 2, 2, 3, 2, 3. Oh yeah, okay, that's correct. So after you get this, then now you can try to see. The question want to see, is it possible for you to travel from A to any other towns, including going back A by using walks of less than 3? So how do you know that whether it's possible or not? So it's by looking at whether you have none of the 0 in the column. So you can see you travel from A, right? So which means that you are looking at the row A. So when you're looking at the row A, then you check. From A to A, there are 6 routes, either length 1 or length 2, that allows you to travel from A to A. The 2 here means that there are 2 walks of length 1 or 2 that allows you to travel from A to B. So the 4 here means that there are 4 roads that are with the length of 2 or 1 that allows you to travel from A to C. For 3, then which means that it's the same thing. You have 3 routes with the length of 1 or 2 that allows you to travel from A to D. So which means that you are able to actually reach all these destination by using a walk that is less than length of 3. So that's why in this case, then you can just answer that is no 0. Okay, there's no 0 entry in the row A. Okay, which indicates traveling. Let's go back to the question. Is it possible to travel from A? Okay, so which indicates that it is possible to travel from, I mean, you do not really need to write that long lah, so which indicates that it is possible, then you can stop. Okay, or you can write possible. Yeah, sorry, I should just do this. Possible, there is no 0 entry in the row A, which means that by looking at this matrix, then you realize that you will be able to reach any other town from A by using a walk that is less than length 3, which means length 1 and length 2. Okay, so that's the idea for this question. So now let's move on to the last example. All right, question 4. The bus routes between the landmarks A, B, C, and D are shown in the graph. So construct an adjacency matrix. So same thing, I think you can do this very quick one. So same thing, I'll try to fast forward. Alright, so move on to part 2. Find m square. Determine all the walks of length 2 in the graph. Okay, so now let's try to do that. So remember, when you are doing your part 1, make sure that your matrix here is not like symmetrical about leading diagonal that you have in part A, because this is a digraph. Okay, so B, let's try to calculate it in our calculator. Same thing, I will try to fast forward the process. You should be able to do it by now. Let's copy the matrix. Okay, let's go back to the question. So determine all the walks of length 2 in the graph. So from the matrix of m square, you know that there's only walks of length 2 exist from A to C, which you have 3 walks here. Other than that, it's all 0, which means in other words, it's not possible for you to reach any destination from B, C, or D by using a walks of length 2. Okay, simple in that. So why is that? So you can check it out. So for BCD, right, then definitely, okay, one example for C, there's no out degree. Am I right? You cannot see any direction that counting out from C. So that's why definitely you cannot have any walk that start from C, then definitely C is going to be the whole 0. Then after that, why is D also 0? Then you can try to check. So for D, right, you have only one arrow that allows you to travel from D to C. But when you reach C, you do not have any opportunity to go to other vertex anymore. So that's why you can't create a walk with length 2. So that's why in this case, you know that this is why D is all 0 as well. So how about B? So when you check for B, same thing. B, there's one arc that allow you to travel from B to C, but you are stuck at C here. You cannot continue. So that's why for C is all 0. So now let's start to check with the one that we only have for walks of length 2 in the graph, which is from A to C. So let's try to see. From A to C, there are 3. So A is here, then C is here. So you can see A, B, C, A, D, C, and also ADC. So there are the 3 walks. There are the 3 walks that give you length 2. Okay, so let's write down our answer. So just now ABC, ADC, and also ADC. Okay, so these are the only 3 walks of length 2 in the graph here. Okay, so now C. Is it possible to travel from A to any other towns, including going back to A, by using a walk less than length of 4? So if you want to find out, is it possible to travel from A to any other towns using walks length of less than length of 4, which means that you should try to find out length 1, length 2, and length 3. And after that, you try to add them all together and see whether there's 0 entry or not. Okay, if there's no 0, then which means that you are able to reach all the other vertices by starting from A. Okay, so same thing, let's try to use our calculator to find out. In this case, we need M1 plus M2 plus M3. All right, so yeah, I'll fast forward the whole progress. All right, so how can you check that? So same thing, we are looking at whether it's possible to travel from A. So we are looking at row A as well. So I'm trying to look at row A, right? Then which means that for 142, which means you are able to actually travel from all the other towns at B, C, and D by using a walks of length 1, length 2, or length 3. But in this case, you are not able to go back to A. Then you can try to check it out because you can see that for all the edges that connects A to the other vertex, they are all going out. So there's actually no edges that going into A. So that's why you can't actually, no matter how many length of walk that you are taking, right, you can't actually go back to A. So in this case then, which means that you can see the 0 here, so you can try to identify that it's actually a no. Okay, so that's a 0 entry. Yeah, that's a 0 entry at row. In this case, it's either you can, so either you want to put it like as k equals to this one, and if you want an easier word, then you can just try to do that's an 0 entry at KAA. You get what I mean, right? Because this is like the whole thing, so you are not able to writing down like 1, 2, 3. So that's why. So that's a 0 entry at row A, column A. So that's why it is impossible to travel from A back to A by using walks of uh walks of length walks less than length of 4. Okay, so I hope that you get what I mean here. So basically when you have 1, then you can see that for A to B, then definitely lah, this is the 1. Okay, then after that for A to C you have 4, then which mean 1, 2, 3, and then 4. So these are all length of walk less than 4, right? Then after that for A to D, then you will have 1 and then the other 1 here. So that's why that's 2. But for A, you are not able to going back, so that's why for this answer is no. So how do you justify? It's because of this place. You have a 0 here, so which means that you can't actually reach A from A. Alright, so I hope that you can understand the idea. So try to spend some time to understand the whole thing. Then after that, to do the exercise. So we are going to having a short discussion about your exercise before we move on to like the test in the class. So no worry, you have a question and answer session during the live lesson next week. So yeah, let me know if you have any doubts as well. Alright, so thanks for watching. I'll see you in next week. Have a good weekend.